Hey everyone, thanks for joining after the lunch hour. My name is Manish. I work for a company called ClickHouse, and today we're going to be talking about when stateful sets are not enough. So effectively, some of the limitations of stateful sets in Kubernetes in the context of operating a database on Kubernetes. Quick word about myself. So I'm an engineering manager at ClickHouse. I work on what is known as the scale team or the auto-scaling team. We mostly deal with vertical and horizontal auto-scaling, idling, which is scale to zero. And in that context, we contribute heavily to the ClickHouse operator to enable those scaling mechanics. Mostly I do distributed systems, databases, and infrastructure. That's kind of the intersection of my day job. And I do compilers in my free time for fun. For those of you who don't know what ClickHouse is, it's an open source column-oriented distributed database. Specifically, it's an OLAP database. So if you have an online analytical kind of real-time analytics use case, a lot of observability-based use cases as well. And many people these days are also using it for data warehouse purposes. So if you're coming off of traditional data warehouses like Redshift or BigQuery, you can use ClickHouse for similar needs as well. Specifically how it works, it's columnar, which means it can leverage really powerful compression techniques as well as all the state-of-the-art techniques in terms of making it very fast. So the performance is a very heavy focus when it comes to ClickHouse. In the distributed system setting, it's a multi-master system, which is going to be important in this context because each replica can ingest traffic. There's no specific master designated as such, and typically like the way you would have it in Postgres or other systems like that. ClickHouse Cloud. So I work for ClickHouse Inc., which is a company operating the cloud product. And it gives you some of these key features. It's quote-unquote serverless. You have idling and auto-scaling. You have separation of compute and storage. So we built our own S3-backed storage engine, which is exclusively used on ClickHouse Cloud. And the way that storage engine typically works is, obviously, your data goes on object storage. But currently, we do have some metadata that we store on persistent volume claims, PVCs, which in turn are, of course, backed by EBS volumes. And there's the bring your own cloud offering. So for people who don't want to provision this inside our own AWS account for whatever data sovereignty purposes, you can provision everything, this entire setup in their own cloud account as well. How does the operator work? Typically, the way it works is every time, if you want to manage a stateful service on Kubernetes, you have an operator. And so do we. We have a ClickHouse cluster custom resource, which is reconciled by the operator. In turn, of course, the operator provisions the stateful sets or a stateful set. And this single stateful set is going to be owning the server pods. Like we mentioned before, there are PVCs bounded to these pods that have the metadata in turn stored on them. And so why is this important in the context of auto-scaling? It's important because, just to give you a bit background, we're going to go back to the operator architecture. But the background here is how does auto-scaling work, right? So you have metrics. It starts with the data that you collect based on the utilization, query log. You have the kubelet metrics, CPU utilization, memory utilization. And all of this data gets stored into a metrics database. Of course, in this case, we also use ClickHouse as that database. And then you kind of have a recommendation engine in there. And this recommendation engine is going to be evaluating a certain time window of these utilization metrics and then creating recommendations based on what it thinks should be your optimal size or number of replicas or whatever that is, right? But this is just whatever recommendation is. It doesn't mean it immediately gets applied. And so you have the second half of the picture, which is the autoscaler. This autoscaler is going to look at these recommendations, what the system thinks based on your utilization, good or bad, where you should be sized at, as well as the user-defined minimum and maximum limits. Those are important because we can never go beyond what the user configures to be the max. If we do that, obviously the user is going to complain. So what this means is if the user has a misconfigured max, we think you should be above that max, we still will never scale you because you probably will get surprised by the bill. And so the autoscaler is responsible for eventually scaling these pods, right? And so let's go into a bit deep into how this scaling happens. So the scaling requires pod evictions. That's been the traditional way it's done in Kubernetes. And so what happens is the autoscaler will one by one evict these pods, and the controller, which in this case is the StatefulSet controller, controlled by our operator, is going to be resubmitting that pod. And when the pod gets resubmitted, it's going to come up in a bigger or a smaller size. In this figure, it's bigger. And why is that happening? That's happening because there's a missing piece of the puzzle here, which is a mutating webhook. So Kubernetes provides admission controller webhooks, and in this case, what happens is every time the pod gets evicted, the controller resubmits, the webhook intercepts the pod spec. So for example, if the pod has a StatefulSet specification of, for example, 10 gigabytes of memory, but the recommendation algorithm thinks you should be at 20, we'll intercept that, and the mutating webhook is going to read that 20 gigs, and then it's going to modify that little resource and limit field. And when the pod gets submitted, it actually comes up with a bigger size. So this, in turn, is actually what happens inside the autoscaling architecture when ClickHouse scales itself, right? The problem is, so this example is vertical scaling. The problem is, this is what we want, right? We want to go from a size, like a starting size of our server replicas, to a destination size. But it requires pressure because, like I mentioned, every time you do a rolling restart, and because we saw here, it's getting evicted, right? So pods are getting evicted. If you evict a pod here, so in this figure, for example, the third replica that is getting restarted, the other two are going to be under even more pressure. So this thing becomes very damaging in case of a scale up where your replicas are already receiving more traffic, they're under pressure, so you decide to scale them up because they're under pressure. And in order to scale them up, you take away the replica to scale it up, which is a kind of a chicken and egg problem. So at the exact critical moment when you needed to add capacity, you took the capacity away to resize it. And the other two replicas, of course, now need to receive that extra pressure as well. So it's not a good situation for anything, right? So you're losing availability. Your existing replicas are also receiving extra load. And we've also seen cases where these extra replicas can also crumble under pressure, under CPU pressure as well. So not a great situation. Slow, disruptive, puts pressure. And actually, in order to kind of combat these kind of scenarios, we decided to allocate a little bit of extra overhead for every replica. So we account for the fact that you have to take away a replica during scaling. So when you provision some size, we actually add like 15% or 25% overhead and provision a bigger size than you actually wanted, which is not good, right? Because ideally, you want your utilization to be as close to allocation as possible. And this happens in a rolling restart fashion. So if you see on the right here, you have maximum unavailable equals 1. That's the pod disruption budget. Because obviously, if you have it any more than that, you cannot have it 0. Otherwise, you'll never get any evictions and you're stuck. And if you have it more than that, then you risk losing even more capacity and availability, which is not good. So this is kind of the best you can do in this break-first scaling model that we call it, because you're breaking a replica before you're making one. And so the alternative is something different, right? There's another kind of, so if you're a Kubernetes expert, you can ask this question: why can you not do in-place pod vertical scaling, which is this beta feature in Kubernetes 1.33? Uses cgroups v2, no restart needed. So why not just use that? The problem is packing. And this is a problem because we use something called the most allocated scheduler to pack our fleet as efficiently as possible when you do bin packing of the fleet. And if you're packing the nodes as efficiently as possible, you by definition cannot always have room to scale in place always, right? So we can see this in this example here. Here, for example, on this first replica, you have enough room to resize it. And so you resize it in place and then you're happy. But now, for the other two replicas, there is no more room on this node to resize this replica. So you have to always, there's no way around evicting this pod because there's just no room on the node. So in-place resizing is best effort. And packing efficiency and in-place resizing are kind of things that are working against each other. And especially in a homogeneous fleet, right? So if you were like a cloud provider, or if you are like running a service where you have multiple different kinds of workloads running inside a single cluster and a single fleet, maybe you can get away with kind of evicting some low priority pods. Maybe not all of your pods here are database servers. Maybe some are like, I don't know, some stateless API servers that you can evict. But in our case, we are just running the ClickHouse database server, so we cannot evict any low priority pods. So it's a homogeneous fleet. So in a heterogeneous fleet, maybe we could do something different. But in this case, we just cannot. So break first model is clearly not working. So we decided to go with a slightly different approach, which is what we call MBB, or make before break. And here the idea is fairly simple, right? You just add more capacity. So as you see on the right here, you had 16 gigabytes pod each. You just add the bigger size pods horizontally almost first. And because of the mutating webhook that we discussed early on, these replicas are going to come up in a bigger size or a newer size. And then you just take away the old replicas. So this gives you immediate capacity, right? There's no more need to kind of evict these pods one by one. There's no need to kind of do it slowly. You can kind of, the problem of putting extra pressure on the nodes, you kind of get rid of that problem as well. And now you can reduce the overhead that you placed on the replicas. So the idea itself is fairly simple. And now we get to the heart of the problem, which is the title of this talk, why this is actually more difficult than it seems to do in vanilla Kubernetes StatefulSets. The problem with StatefulSets is that StatefulSet scaling behavior is actually governed by ordinals, right? So you start with the number 0, and then you have add 1, 2, 3, 4, 5. And that's how you scale out. And when you scale them back in, you also go in the reverse direction. So if you're doing, if you're saying, give me 3 replicas when you have 6, you'll actually go from right to left in this direction if you see the bottom arrow, which means if you're trying to do make before break, if you're adding replicas 3, 4, 5, and then you want to take away replicas 0, 1, and 2, it's actually not possible if you only have a single stateful set. Because the minute you tell it, hey, give me 3 replicas, it's going to take away 3, 4, 5, which are the exact replicas you just added. So single stateful set is kind of tricky to get it right in terms of this kind of behavior. You cannot break arbitrary replicas. There's another Kubernetes feature which can kind of sort of get you there, which is this thing called a start ordinal. So what you can do is you can start with like replica 0, 1, and 2. You can add the third replica, so you've done your make, right? And then you can say, hey, let me kind of shift my ordinals to start, instead of starting from 0, to start from 1. And now what you've done effectively is you've broken the replica, the 0th replica here, right? So you have achieved make before break in a single stateful set using this feature. The problem is, again, it's not flexible enough, because maybe on the 0th replica, you might be running a backup. So that one is not exactly the replica you want to break right now. The second replica is maybe running some long-running queries that you cannot terminate, you cannot afford to terminate. So the only replica that is safe to break is the one you cannot break, because it's an arbitrary one. It's not so the start ordinal feature will only go from left to right, kind of in a shifting window. So it's still not flexible enough to break any arbitrary replicas. So we saw this problem. We kind of looked at like some of the open source projects out there. Yeah, this is the problem, breaking arbitrary replicas. And one key idea that was kind of visible in some of the open source projects, such as the Advanced StatefulSets by PingCap and OpenKruise, was this idea of delete slots. And I really liked that idea, so we kind of decided to kind of steal it. But before that, we wanted to kind of evaluate, hey, are these existing controllers and custom resource good enough for us to use them as is? And yeah, so the idea itself is fairly simple, right? You just add an annotation or some kind of way inside the CR. You tell the CR, hey, this is my delete slot. Please delete this replica. And then you just write a controller with some custom logic that can just delete this replica. With the PingCap project, the Advanced StatefulSet project, the problem was that it was quite experimental, and still it falls back to the ordinal behavior. What I did not want to have is, like, you can imagine, do this process like, I don't know, 10 times a day or something, and then you end up with like arbitrary numbers in your replicas, right? You have replicas, pods 41, pod 47, and pod 49. What explains those numbers? It's kind of confusing. It's very unintuitive which ones are supposed to be there if you're debugging a problem and kind of trying to decide which replica should be there, which replica shouldn't. Ordinals are just going to add to the confusion. They're not going to remove that away. So we did not want to kind of deal with that. OpenKruise was a second project that we evaluated. They've got like some extra nice third-party controllers, like another one called Advanced StatefulSet, but different from the PingCap one. We had the same problems with the OpenKruise Advanced StatefulSet as the PingCap one, but the clone sets were all kind of the replacement for deployments. There we had different challenges, and the challenges was that you can either modify the resources, which is what you need for scaling, or you can modify like the PVCs, the delete and retain the PVCs. You cannot have both of them. But in the context of scaling, we wanted both, right? We want to retain the PVCs for metadata, and we want to resize our pod. The other problem was that we already have a fleet running on these single stateful sets, and it's really difficult as a migration to migrate production customers to go from one CR to another kind of CR with a separate controller, which is not exactly in our control. It's a third-party controller. So it was kind of a bigger risk. So we decided not to use clone sets. So the problem set at this point is pretty clear. You want to have something like a stateful set, but you also want to have the flexibility of breaking arbitrary replicas. You want stable identity, and you don't want like ordinals, right? Because ordinals are bad. So we decided to just use random suffixes, kind of like a deployment would. Delete slots are something that you need. We need to think about topology, spread constraints, PDBs, all those things. And the idea and the solution was fairly simple in this case, which was something we called multi-STS or multi-StatefulSet. And it's very simple, right? So just leverage the vanilla stateful set, but go from one to many. Very, very simple idea in like when I describe it. But what you do is you just have one stateful set per pod. And this is what it looks like, right? So before we had a single stateful set controlling 3 replicas. And these 3 in turn are obviously ClickHouse server replicas. And in the next stage, you can just add a multi-stateful set approach where you have 3 different stateful sets, each controlling their own replicas. And now what you have is you have the flexibility that you can do make before break. You can add arbitrary replicas with a make step because everything is in your code and it's inside your operator. And then you can just condemn, break, do whatever you want with any arbitrary replicas because everything is in your control. But it gives you something which we've been internally calling like the quiescent state. You still want to have the stateful set controller managing the pods. A lot of Kubernetes-based stateful projects tend to go with managing their own pods, like bare pods. That's a little bit risky in my opinion, because with this approach, you can still have a downtime. If you introduce a bug inside your operator, that doesn't mean the stateful set controller will stop managing the pod. So you will avoid downtime. I'm sorry, not introduce downtime, but avoid it because even if you, unless you doing something really stupid, the stateful set controller is always going to be managing the pods themselves, and you're going to be good, right? So, but if you, on the other hand, if we were managing bare pods ourselves in our code, every time we write the operator code and upgrade the code, we'll have to be very careful about upgrading things, because what happens if I introduce a bug that in turn just deletes my pod? But yeah, so this is make before break using a multi-stateful set approach. And yeah, so the final step of this project was, of course, migrations, because introducing stateful sets and going from this single stateful set to multi-stateful set is still a difficult project. In our case, we have like a fleet of thousands and thousands of single STS clusters, and they need to be migrated, right? So that they can leverage this better, faster mode of scaling. So no downtime, obviously a requirement of the migration. You need to have something to orchestrate it, something to organize it, make it visible to the customer, etc. And because this kind of an approach will come with its own cost, ClickHouse as a database, it's not really trivial to add and remove replicas. So when you kind of do that, it introduces new failure modes that the database has not dealt with before. So you need to be able to think about it and combat it. And of course, you need to be able to roll it back. So this is kind of like, in a funny way, we decided to, what it ended up looking like was make before break, which is the feature that is being the end goal of what we want to power it to, ended up being the mechanic of migration itself as well, right? So what you have is, this is the existing picture, right? So you have like a single stateful set managing 3 pods. What you do is, you just add 3 new stateful sets, each in turn managing its own pod. So now you're in a mixed configuration with both single stateful set and the multi-stateful set mode. And then you just kind of do a synchronization, because all of these 6 pods are part of the cluster. The metadata gets replicated for all the replicas. And then you just get rid of or break the single stateful set. So in a way, you're doing MBB to do the migration, right? And when you get rid of it, all you're left with is the new orchestration way, and the old orchestration way is no longer there. So if you do this across your entire fleet, you have moved every customer from the single stateful set mode to this new one. And this is what we ended up implementing. But you still need some sort of a coordination strategy here, right? Because you have an operator which is responsible for reconciling the single stateful set. So you need something to say, hey, stop reconciling that single stateful set, add these new replicas. It cannot be your operator because the operator is kind of doing its own thing with the existing customers. So what we ended up doing was creating like a Temporal. I don't know how many people here are familiar with Temporal, which is like a durable execution workflow engine. So we leveraged Temporal to do this orchestration, and we implemented like a custom Kubernetes controller to implement this migration. So Temporal, yeah, it's a durable execution, kind of a DAG sort of a system, preserve state. I really like it because there's no need to explicitly persist your inputs, outputs. It's already preserved. It gives you like, you start with an initial cluster state, gives you failure detection, gives you retries, scheduling, everything out of the box. So implementing any sort of a migration or any sort of a workflow is very, very easy in Temporal. And this is what it looked like. So you have like a maintenance watcher. We put the cluster in the maintenance mode. And then every time a cluster which is scheduled for maintenance comes up, it sees, okay, this is the cluster that I need to migrate today. Maybe you have like a batch of 10 clusters being migrated every day. You spin up like a child workflow for each one of them. And then you kind of kick off, kind of push down a signal to your Kubernetes controllers that, hey, this cluster needs to be migrated. So please do this whole dance of adding new stateful sets and removing the old stateful sets with this cluster, please. And then tell me when that dance is finished and then your cluster has been migrated so that I can inform to the control plane, to the UI, that your cluster migration has been finished. So yeah, workflows, this is just more temporal. So if you don't know it, deterministic sequence of steps can be interrupted, can be resumed. This is a really nice property, by the way, because it allows for human intervention. Because what can happen is that maybe you get stuck in a migration and you need to send a signal to a human, and someone needs to go on call, go inside the cluster and debug some things and kind of kick the migration along or kind of reverse it. So all of these things were possible with using workflows and activities. Activity is basically like a unit of work inside a temporal job when you're kind of writing it. And this is kind of what it looks like, right? So you're kind of waiting for events, and you get like a really nice UI with the outputs of what's going on inside your instance, what stage of the workflow progression has been made so far. Yeah, and this is kind of an example of human intervention, right? So we detected like some configuration drift when we were doing the migration, and so you send a message on Slack, someone debugs it, someone updates the configuration, and then eventually all of these things can get sorted out. And the custom controller itself was also an interesting kind of part of things, because it's really a test in how to scale ClickHouse, which was not like ClickHouse as a database has been around before Kubernetes. It wasn't really designed to be cloud native. So moving it in that direction, making it more elastic, has been an interesting challenge. So a lot of failure modes like synchronization of the catalog, synchronization of the part metadata were things that we discovered when we were doing these migrations. So every day we would kick off a few migrations, and once in a while we would encounter like a bug, and then we will fix those bugs. So let's discuss some of those challenges of the database itself. Right? But before that, so yeah, migration controller itself, like I said, the way it works is you just start with like a label selector on the CR. So you add a label to the CR and say, if this label is present, just kick off the migration controller will start reconciling and adding those stateful sets to the cluster. And the way it works is it works through a mutex, right? And you need this mutual exclusion because you cannot have both the ClickHouse operator, which is the primary controller responsible for reconciling those resources, and the migration controller reconciling the same resource at the same time. So you need to have some sort of exclusion there. And then what you do is, after that mutex is in place, you just hand over the responsibility during the presence of the migration to this controller, which is going to be adding those multi-stateful set replicas, and then going to be removing the single STS. And now you're in kind of this, after the mix mode is done, you're in this secondary mode of operations, which is this multi-STS mode, and then you hand over the control back to the original ClickHouse operator. And so the migration controller itself was effectively like a wrapper controller. What it was doing, the clever thing was that even though it was a separate controller, it would call into the operator because you still need to do a lot of the basic features of the operator, right? You still need to be able to provision users. You still need the ability to scale. So all the standard responsibilities of the operator were still there, but it was being done in a different workflow as part of this controller. So if you see here, you have like the operator reconciler, the second last piece of line. So you have a reconciler inside of a reconciler, right? So that's what it's doing. And there's some sort of coordination that is being done by the snapshot controller here is kind of like a nice safety blanket. Because we have PVCs, if something goes wrong during the migration, we want the ability to be able to kind of snapshot those PVCs, restore them, and then kind of do some manual recovery operations just as a data safety guarantee. But yeah, wrapper controller does the make, does the sync, does the break, and then is backwards compatible. Making ClickHouse more elastic, yeah. So some interesting challenges that came along our way was the one I really like is this topology spread constraints. So the way we provision our ClickHouse clusters is that in a 3-replica setting, you have like 1 replica available in 1 availability zone. So as you're adding and removing these replicas, what you can have is you can have like a zone imbalance, right? So in this example, for example, we have 4 replicas, 1 in zone A, another in zone B, and 2 replicas in zone C. And this is a valid topology because your max skew is set to 1. But then when you, let's say you're doing make before break, and you break these 2 replicas because maybe the ones in zone C were the new ones, the ones that were just made, and A and B are the ones you're about to break. So when you break them, suddenly your zone topology becomes invalid. And yeah, these challenges are kind of interesting. And now you kind of have to figure out, oh, which zone am I not provisioned my pod in? And then maybe I need to kind of do some workarounds as part of on-call. Another problem was that, for example, we have something called scale to zero idling. What happens is when you're idling, your PVCs are kind of still lying around, right? And your PVCs are associated with certain availability zones. So what happens when you're idled and your customer decides to say, you know what, instead of 3 replicas, I'm going to have 4. And so when you wake up, don't wake me up with 3 replicas, I want 4. And now you're in this situation where a new replica has just come up, but because the Kubernetes scheduler is not really aware of the PVCs, it's only aware of scheduled pods. At this point, there's nothing scheduled. You can have a race condition. And the race condition here is you have like AZ A, AZ B, and the third one also goes into AZ A, right? This new replica also comes up with the same zone. But now you have a problem because they land on the same AZ, and you kind of break your skew again. So scaling out and idling is these kind of situations with you have like unschedulable pods because of these race conditions can be very tricky to solve. And all of this, by the way, this particular condition happens because the Kubernetes scheduler doesn't really care about the PVC zones. It's just aware of the pods, like I said. So all of these problems were solved by what we call zone pinning. Basically, don't rely on the scheduler to pick the zones. Do these things yourself as well. So kind of store the state of your AZ zones, and then every time you're adding or removing replicas, recompute the zone balance, and then pick whichever zone does not have a pod inside it, or whichever one has like the least number of pods. So kind of pick that one to provision your pod in. Yep, I think this is mostly, just a summary of what I just said. You just end up managing the topology yourselves. Some more interesting things as part of making the database elastic. So ClickHouse has what you call external database engines. So you can create like a database or a table with like a source which is actually pointing to like a Postgres or a MySQL or a Delta Lake, whatever. The problem is a lot of these kind of third-party systems can end up becoming deactivated. Customers have forgotten about them. The database is no longer around. But then when you do these kind of scaling operations, suddenly these new replicas, when they try to connect, they fail, and then they get into these weird states. So we ended up fixing some of these issues as well inside the core database. And the similar problem also exists with materialized views. So you have like a materialized view, which is going to do some transformation and then dump the transformed data into the final table. But it's the source table can just get deleted. So it's kind of the same problem. So when you do an MBB or when you do a migration, you will not be able to recreate because the source table is gone. So these problems were eventually also fixed by the core database itself. And this is, again, a very interesting problem, which is unbreakable replicas, right? So because you're doing make before break, what you want to do is synchronization of the catalog, right? So that was the kind of original thing when we had the sync step inside our MBB operation. So you have inserts coming into these 6 replicas at this point. And then what you do is, because as part of the migration or as part of MBB, you remove the single stateful set. So you remove replicas S1, S2, and S3. So inserts are no longer going into these replicas. The new customer inserts are only going into the green replicas, right? And then at some point, we run this system command called system sync replica lightweight. And this command is meant to kind of copy over the catalog and kind of wait for all the synchronization to happen. The problem is, if you're only, unless you're specifying which replicas to wait on, it's going to wait on all replicas, right? So in this case, M2, the purple replica, is not only going to wait for inserts and synchronization to happen from S1, S2, S3, but it's also going to wait for the synchronization to happen from M1 and M3. And so this way, it will wait forever because M1 and M3 are always going to be around because they're part of the new replica set. They're not part of the old one. So it becomes unbreakable. To solve this, basically what you need to do is you need to add like a from modifier to the SQL statement where you say, hey, instead of synchronizing from all the replicas, you only expect and synchronize from S1, S2, and S3. So add this as like from source replicas and as an explicit modifier inside the SQL statement as well. So we had to make this change inside the core database. And now after this change landed, the synchronization kind of works correctly for the right set of replicas. Yeah, some issues with DNS happens all the time. Like, a data gets inserted with their host replica names inside the distributed DDL queue, but that replica is no longer around, so the DNS is failing. You kind of have to fix that. System tables, which ClickHouse keeps around internally for customer telemetry. We had to kind of stopgap solution do insert select because these system tables are replica local, but we needed to kind of introduce a new disk type just so these system table data is also backed on S3 and not just on the replica local PBS volumes. But yeah, summary, migration of these 1,000 clusters, really, it's not a trivial problem. You do some migrations, you find some issues, and you fix them. Do it on a weekly basis. There's special requirements and special white glove handling for critical customers. But yeah, migrating of the entire fleet took us over a year. And in my mind, this is kind of like, I'm really proud of how we ended up doing this because it's kind of a product reputation thing. Whereas you're doing a lot of these synchronization problems and scaling problems, you're dealing with them without even allowing for like a downtime or even a partial downtime. All of your inserts and selects are still working. And so that makes it all the more tricky and a lot more difficult to execute. Because if you end up with like even one slight bit of problem with like, hey, my data is gone, now suddenly you're, especially in the database world, I think most people who work in this industry will know that it's your reputation is entirely about how reliable your database is, and we cannot afford that. So that was kind of a really nice moment where the migrations ended up finishing and we were going from the old stateful set mode to the new one. And yeah, the final thing is, yeah, stateful services on Kubernetes have always been hard. I don't think anyone doubts that. But some of the examples in the open source, like Cloud Native PG and Strimzy, as examples of projects that have solved the same problems with the ordinals or with bare pods. And, so it's kind of, this is not exactly very novel, but like if you're doing this stuff on Kubernetes, you'll probably run into these challenges. And that's it. Thank you so much for your time.
Thank you. Thank you, Manish. Any questions for Manish? Yeah.
Yeah, so the question is, I think you showed some very cool ideas here, and any of those are available as an open source code?
No, we are working on an open source operator, I believe, but I'm not sure of what the timelines for that are. These ideas are, because I'm part of the cloud team, so my job is really as a product to focus on what ClickHouse Cloud sells. So it's not open source.
Okay, thank you.
Yeah.
Thank you. Another question? No. Let's thank again our speaker for a nice presentation. Thank you.
Thank you.